Welcome to Hot Chips 18. Session 4. Reconfigurable Computing.
Very happy to introduce the speakers for this session on reconfigurable computing. We have three really terrific talks. The first speaker is Peter Alfke from Xilinx. Peter is a distinguished engineer at Xilinx, where he's been since 1988. Prior to that, he worked at a number of companies, including Fairchild, Xilinx, AMD, and others. If you've used Xilinx FPGAs, you'd recognize Peter's name from the numerous application notes that he's authored on Xilinx FPGAs. He's also a regular contributor to comp.arc.fpga. So Peter's going to talk about the latest and greatest FPGA from Xilinx, the Vertex 5. Based on 65 nanometer technology. Peter?
Thanks, Tom. So I've been at Xilinx for 18 years, and I've been involved in many product introductions. The latest one was Vertex 5, which we introduced earlier this year, and we've been shipping for a couple of months or a couple of weeks. We have several of these devices available. So let me give you an overview over my talk. The structure is I want to talk a little bit about 65 nanometer technology, because Vertex 5 is still the only FPGA in the world that uses 65 nanometer technology, and a little outlook what happens in the future. And then I'm going to talk about the ingredients, about the components inside the Vertex 5 family, and a little bit of benchmarking, and in the Xilinx fabric, and we are going to talk about several of the ingredients that we have in the chip, and then there is the obligatory conclusion. So a little bit about our 65 nanometer technology. It's manufactured at two places. We believe in a two-source strategy. So we make these devices, we have these devices made at Toshiba in Japan and at UMC in Taiwan. The process is a state-of-the-art process as used in microprocessors and logic devices. The peculiarity that we use is that we have three different thicknesses of the oxide. And so everybody, of course, at 1 volt uses thin oxide, 16 angstroms in our case, and everybody that wants to interface with the rest of the world uses thicker oxide in the I/O, because we still have to be 3.3 volt compatible. But what we did differently from other people is we used a thicker oxide in the 1 volt core, and that thicker oxide gives us much, much lower leakage current. Now, of course, we use this thicker oxide only on the transistors that don't have to be fast, and there are millions of transistors in an FPGA where we are glad that they're slow. They're the ones that store the configuration. So we take advantage of that and achieve considerably lower leakage current. Xilinx has always been driving process technology. Here we see the progress over the last years, and it's natural for our customers. They always want us to be bigger, faster, and cheaper. And that's what Moore's law, of course, provides. And that's why I've been riding down this curve from 180 nanometers to 90 nanometers in the previous generation to 65 nanometers now. And it is no secret that our designers are presently working on 45 nanometers for, let's say, 2008. And in 2010, perhaps we even have, hopefully, we have 32 nanometer. So if you're not happy with our devices, you think they're too small, too slow, and too expensive, Just wait a couple of years. Moore's law really works for us. Now, it's always fantastic what can be achieved, but there also are problems. I think marketing says there are no problems, there are only challenges. Challenges are that we have higher leakage current as we decrease the size of, and as we get to a thinner oxide, we run into considerably higher leakage current and therefore higher standby power. And that's something that everybody in this industry is fighting, when we had several papers about that today. Lower supply voltage is good, but it also means that we need very, very good decoupling capacitors. As you have 1 volt of supply voltage and multiple amps of dynamically changing current, you want a low inductance decoupling capacitor. We struggle with 3.3 volt compatibility. Thank God we gave up 5 volt compatibility a long time ago, but 3.3 volt is a challenge for these modern processes. And another challenge is the heat density. Chips are getting small, they run very fast, and so you have lots of watts in a small area on your PC board. And 1 billion transistors do create heat. On the chip, we have 12 layers of metal. In the package, we have another 10 layers of metal, and you on your PC board have another 16 layers of metal. So there's an awful lot of metal that the electrons have to travel through. And the last problem is that we have signal integrity issues on the PC board. The transistors are getting faster, currents are getting higher. 2 volts per nanosecond is a typical ramp rate on the output, and 50 milliamps per nanosecond. So those values really mean that you have to be quite careful how you lay out your PC board. So the chip is complicated, the package is getting complicated, and the PC board is getting complicated, and that's why we need smart engineers like the people in this room. So Xilinx introduced something in Vertex 4 that we call assemble architecture, which is a layout methodology on the chip. We used to scatter things about, and we had the I/O at the periphery. Nowadays, we arrange our functions in columns. So there's a column for logic, there's a column for memory, there's a column for I/O, multiple columns for I/O, and there's a column for special IP. So this architecture allows us to scale and to come up with a multitude of subfamilies, which I'll explain in a moment. It also makes it easier for software and hardware to interact. And last not least, it allows us to scatter the I/O all over the chip, which means we have less inductance when we reach the PC board in the ball grid array. So there are many advantages that we can get from this way to lay out the integrated circuit. So thanks to this method, we managed to have 4 subfamilies. Vertex 5 really consists of 4 different families, and we call them LX, which is logic-oriented, which is the basic family, the one we are presently selling. And it has a lot of logic, it has a lot of memory, it has parallel I/O, quite a number, many, many hundreds of pins. There is going to be soon an extension of that family. It's called LXT, and the T stands for transceivers. And so this family is the same as LX, but it has a bunch of multi-gigabit transceivers on the chip. There's another family, SXT, which is very similar, uses the same ingredients, but it has a different mix between logic and DSP, multiplier accumulator, and RAM. So the actual ingredients are the same, but the mix is different. Less logic, more multiplier accumulators, DSP circuits, and more memory. And finally, there's FXT, which has PowerPCs and even faster multi-gigabit transceivers. So as a total, the family will have 17 members, and it's only because of this columnar architecture that we managed to design these, and we managed to keep the software under control to handle all of these devices. 17 devices in one family. So this is a slide I borrowed from marketing. Marketing likes to talk about all the fancy ingredients that we have on that chip. And I will not talk about all of them, but I'll talk about 3 of them: the lookup tables, the memory, and the SelectIO. So let's take a look at the lookup tables. When 18 years ago, Xilinx started to pioneer the use of lookup tables for random logic. And in those days, there were extensive studies to figure out what's the right size of a lookup table. First, we had a 3-input lookup table. Then academic and our own investigations showed that a 4-input lookup table was the optimum size. A 4-input lookup table has 16 bits. Now, 18 years of Moore's law later, the lookup tables laid out very, very nicely and compactly, but the rest of the chip has grown. There's far more other miscellaneous features on the chip. And so the 4-input lookup table looked suboptimal. And we took a hard look at it and said, let's try a 6-input lookup table, a 64-bit ROM instead of a 16-bit ROM, which sounded very aggressive. But then we looked at the layout, and the layout increased the chip size, or the CLB size, by only 15%. So a 4 times larger lookup table made the CLB only 15% larger. And then we ran benchmarks and said, how much logic power can I get out of this lookup table? And we found that it is 40% better than the 4-input lookup table, so factor 1.4. Now, 40% better for a 15% price increase seemed like a good deal. So we went to 6-input lookup tables. And the 6-input lookup tables, in actual fact, we went to a 6-input lookup table that also can be used as 2 5-input lookup tables with the same address input. This also increased speed because we can pack more logic into the lookup table. We will, in certain cases, have fewer levels of logic, which also provides a higher speed. Now, we use the lookup table. We have, for a long time, used the lookup tables as distributed RAM. And when you use these lookup tables as distributed RAM, of course, we get the full benefit of being 4 times larger. So these lookup tables are now 64-bit RAMs. And we also use those RAM-oriented lookup tables as shift registers. And as shift registers, they are 32-bit long. You remember the SIL16. It is now an SIL32. And it can be used as either a 32 1-bit long shift register or a 2-bit wide 16-bit shift register. Now, not all lookup tables have the memory feature. We found that not everybody needs every lookup table as memory, and so we cut down on the number of lookup tables that can be memory, and it's about half the lookup tables on the chip can be memory. Just to give you a feeling for how many lookup tables there are, in the smallest of the Vertex 5 parts, it's 20,000, and in the largest of the Vertex 5 parts, it's 200,000. So, okay. Routing is one of the most important ingredients in an FPGA. The joke is that you pay for the routing, we throw in the logic for free. Therefore, it is very important to have fast routing and universal routing. And FPGAs have often been criticized that they're not fast enough. And this is the routing structure of Vertex 4. To give you a feel for it, each of these squares is 1 CLB. So each of these squares is 8 lookup tables. And the different colors indicate how many hops, how many concatenated lines it takes to reach another lookup table or CLB in the neighborhood. And this was Vertex 4, which was not so bad, and this is Vertex 5. So in Vertex 5, we have a very regular structure where you can reach lookup tables or CLBs in the vicinity with very few hops. Now, what is a hop? A hop costs about 200 picoseconds. It's a piece of metal with a buffer at the end, so it is fairly insensitive to loading. And so for 200 picoseconds, you can make one of these hops. And I've counted the CLBs that you can reach. It's about 270 in about 600-700 picoseconds. So you have a reach of more than 2,000 lookup tables that you can reach with considerably less than 1 nanosecond. So that should make the layout of the chip, the speed, considerably less sensitive to placement. The next ingredient in Vertex 5 is the memory. And memory is very important. We have to have the right size and the right features. So the BRAM, block RAM, as we call it, in Vertex 5 is now twice as large as it was before. It's 36 kilobits, not bytes. And it can be divided into 2 halves. And each of these halves, or the whole block RAM, can be configured in any aspect ratio that you want. You can make it 72 bits wide and only 512 addresses, or you can make it 1 bit wide and then you have 18, or in the whole memory 36,000 addresses. The interesting thing, each block RAM is a dual ported structure. It has 2 ports, and you can configure either port any way you want. So you can come in 72 bits wide, and you can go out on the other port 1 bit wide. So that's a flexibility that we have supplied there. The 2 ports have nothing in common but the central data storage. So they have independent clocking, independent enable, independent addressing, independent data, and so you can configure this in many, many different ways. We found that many people use block RAMs as FIFOs, first in, first out memories, and so we decided to make life easier for the user and put a FIFO controller inside the block RAM. So this block RAM has one FIFO controller, which can control the whole block RAM or can control 1/2 of the block RAM. It runs, the FIFO runs at 550 megahertz and runs with synchronous or asynchronous clocks. So you can build an asynchronous FIFO running at up to 550 megahertz on both clocks, and the clocks can be asynchronous. And we have tested this very, very thoroughly. We have a long experience in building FIFOs, and so we think that it is considerably easier for people to just use the FIFO so they don't have to design the innards. The other feature that this memory has is it has Hamming error correction. So if you configure the block RAM 72 bits wide, you have a Hamming controller inside the block RAM, and so you can detect double errors and correct single errors. And you have a choice whether you want to correct only the output or whether you want to do scrubbing. So when you detect an error, you correct actually the content of the memory also. And as a very, very nice feature, you can use this ECC circuit even when you interface to external memory. So the ECC circuit can control external memory, correct errors, do scrubbing, and so on. It costs you the 2 block RAMs inside the chip where the error correcting circuit is located. An important feature of any FPGA is I/O. And surprisingly, I found it surprising, the I/O is often faster than the innard of the chip. So the I/O, nowadays we handle 1 gigabit per second in the I/O circuits. the idea in Xilinx is, our religion is that all I/O pins are created equal, endowed by their creator, by equal drive, equal functionality, and equal features. This is a subtle hint at our competition. So all pins are the same, except the power supply pins. And so they can be configured for about 40 different standards. They can be differential, single-ended, high drive, low drive, 3.3 volts, 2.5 volts, 1.8 volts, and so on. So there's about 40 standards that each of these pins can have. And also, each pin has dedicated circuitry in it that allows series termination and allows various things listed on this slide that I will describe in the following slides. So the idea was to be compatible and well-suited for source synchronous I/O up to 1 gigabit per second and a little bit faster. So the first thing we put into the I/O is we gave every pin a variable speed delay element. So there's something that we call I delay. It's a tap delay line on every pin. The tap delay line is servo-controlled and stabilized. That means we look at the 5 nanosecond delay line and compare it to an oscillator and adjust its internal supply voltage such that the delay is 75 picosecond per tap. So you're not exposed to temperature changes or processing changes. So you have an input delay that you can choose to be any multiple of 75 picoseconds. And you can dynamically control, so you can, for example, adjust to changes on the PC board. You adjust to delays through a connector. You can adjust to reach the middle of the I pattern. And so this has become a very popular feature. It was already available in Vertex 4, and it has been improved in Vertex 5. The next feature on every input is that we put a serial to parallel converter in it. As I mentioned, the circuit, the I/O circuit, runs faster than the interior. So very often you use internally wider buses, and you can run 1 gigabit per second on the output. The same thing happens on the output. We have a parallel to serial converter, so you can run slower internally and get to faster serial output. Okay. So in order to prove to ourselves that Vertex 5 is a good architecture, we decided to run some benchmarks. And the first benchmark here is an MPEG-4 video decoder. And thankfully, this morning, the people from Philips explained exactly how an MPEG-4 decoder runs, so I don't have to do that. As a parser, there's inverse prediction. And this circuit, we put the circuit into a Vertex 4 and in a Vertex 5. And we wanted to find out how much the Vertex 5 is better. Now, we needed a reasonably large circuit, so we picked this one. Next effect, it wasn't large enough, so we put 8 of these into a middle-of-the-road Vertex 5 chip. So now we have 5 MPEG-4 decoders, and let's see what happens between Vertex 4 and Vertex 5. So as you see up in the table on the right-hand side, the number of, if this thing worked, would be nice. In the table on the upper right-hand corner, you see that it took 67,000 lookup tables in Vertex 4, and it takes only a little bit over 40,000 lookup tables in Vertex 5. So it is a 35% improvement. But the improvement isn't the same all over the place. You see on the left here, the adders, subtractors in the circuit, for example, you don't gain anything by going to 6-input lookup table, neither the counters or the comparators. But in the multiplexers, the memory, and the miscellaneous, we pick up an enormous improvement using the 6-input lookup tables. And here we show that our software actually did use the 6-input lookup tables very extensively, and so the software is capable and the synthesis is capable of performing that job. Another feature that gives us great improvement is that we can use the 4 lookup tables that are together in a slice as a quad-port memory. So quad-port memory are difficult to build, and they are popular in register files in microprocessors. And here we show that the 4 lookup tables in one slice can be used as one address and one write address and 3 read address memories. And so that structure is being used in the new Microblaze 5, which was redesigned for the Vertex 5 architecture, and it makes better use of the LUTs. It considerably reduces the size of the register file, but it is groomed for high speed. We wanted to achieve the highest speed, so actually the number of lookup tables increased slightly, but we went from less than 1 DMIP per megahertz to over 1 DMIP per megahertz, and we made the clock rate 10% faster. So this microprocessor now is almost 40% faster than its predecessor. Here are benchmarks, and the benchmarks show that Vertex 5 is about 30% faster than Vertex 4. This is a comparison to ourselves. It's not a benchmark against a competitor where people often play dirty games, so we have no reason to do that. Vertex 5 is, on average, 30% faster than Vertex 4. So, in summary, I talked a little bit about the technology, about 65 nanometer technology. We talked extensively about the improvement in the I/O pins. We talked about the 6-input lookup table, and we demonstrated that in benchmarks that the superiority of the Vertex 5 over Vertex 4. And this is a work in progress. Vertex 5 is a work in progress, and we are introducing several new chips, several new part families in the next weeks and months, and something even early in 2007. This is a table of the features. So I hope this hasn't come across as a marketing presentation, and I thank you for your patience.
Most of the talks you see here at Hot Chips are about real products, or at least real prototypes. And we work hard to make sure that that's the case, that the papers get in and describe real products. Once in a while, though, we have talks that are about new concepts or emerging ideas. And so I think the next talk is in that category. This morning, Justin Ratner did a really good job of making the case for why it's important to start looking at highly parallel applications to drive the research in new architectures. So this next talk is about one approach, our approach at kind of looking into the future of thousands of processor cores and figuring out a way to make progress on the application, the software, and the architecture space there. This is a collaborative effort. As you can see by the list of authors here, it's unusual in the sense that it has collaborators from all over the country. We thought about who should give the talk for about a microsecond, and we decided it should be Dave Patterson, because I believe you all know Dave. He requires very little introduction. He's a professor at UC Berkeley, where he holds the Pardee Chair in Computer Science. He's probably best known for being one of the key people behind RISC, RAID, Now, and also co-authoring with John Hennessy the probably most popular books ever in computer architecture and at the graduate and undergraduate level. Okay, Dave?
All right, thanks. We know exactly when this project got started. This project got started exactly at the Computer Architecture Conference in Madison, Wisconsin. A bunch of us that are on the slide were talking in the hallways instead of being at the talks. I'm sure there are people out there right now. You know, what are we going to do about this microprocessor parallel revolution? What are we going to do about that? And every day the ideas got more and more exciting, and by the third day of the conference, we came away with an action plan and formed a cabal to work on this. And when I got back to Berkeley, we looked at the B2 stuff, and it looked like a perfect match to what we wanted to do. And so within, Monday we were blue skying ideas, and by Friday we had 10 people signed up to try and make this happen. I highlighted people who are here in the audience today. It's kind of hard to go to a talk in computer architecture without having people in the RAMP project involved. There's 10 people at 6 institutions. Thought I'd set the stage, introduce Ratner's keynote address a little bit later. Why is all this parallel stuff happening, and then what are we going to do about it? So conventional wisdom in computer architecture is the good old days. Researchers would build chips to demonstrate ideas, and there were chips here by researchers in the good old days. But the cost of ECAD, the cost of mass, and these exotic circuits needed for the high clock rates mean most researchers can't believe believable prototypes anymore. Continuing that old conventional wisdom, new conventional wisdom style from US News World Report, the good old days, power was free and transistors were expensive. I was always amazed we could keep increasing power and nobody said anything. But now we've got this power wall, which everybody talks about. The old days, it was multiplies you had to avoid. It was the memory access is fast. Now we've had a power wall we've been living, memory wall we've been living for a long time. And good old days, we would innovate at the instruction set architecture, compiler interfaces, and extract more instruction level parallelism to make things go faster, keep up with the doubling every 18 months, and we ran out of that. So guess what? Power wall plus memory wall plus ILP equals brick wall. Fortunately, as John said, by working on textbooks for a long time, you can go back in the old versions of textbooks and put it all together, and here's our history. Those of us who've been around a while, the good old days, the VAX days, we remember that fondly. Amazingly enough, the VAX didn't get any faster for 6 years, and nobody said anything at the time. We thought it was great. Then the RISC stuff came along, and that really did spark this revolution. And this is various generations of the spec int over all of its years that we've concatenated together, and it really did double every 18 months for 16 years. And for those of you who weren't paying attention, that last year was 2002. And since then, it's, I don't know what the hell it is, but it's certainly not 52% a year. If what I expect to happen by the end of this year, we'll probably be off by a factor of 3 of that doubling every year. So what's happened is this shift to multiple cores rather than performance for a single core, and the whole industry shifted that way. So this is kind of, with that setup, here's the rest of my talk, which will talk about RAMP. So what's wrong with these multi-core, or even if you're going to not go from a few cores per chip to dozens or hundreds or thousands of cores per chip, what's wrong with the many-core design is no one's ready for it. None of the pieces of the software stack are ready for 1,000 processors per chip. As I just said, the researcher community can't really build the chips anymore. We got to get them from companies. And software people don't start working until the hardware shows up. That's just, all of my career, that's the way it is. It's possible some of us hardware people may have promised things before they actually arrive. You know, start now, start using the simulators, it'll be here tomorrow. Well, maybe their experience hasn't worked. Plus, once the hardware's there, the hardware's so much faster than simulators, as they can get more work done in a couple of months after the hardware shows up than years of simulator time. So that's what they do. And in fact, after you do your design, you get it there, the hardware shows up, and 3 months after it's there, they tell you everything that's wrong with it. So you wait, you go away, and you come back 4 years, and you get another 3-month window, and they'll tell you what's wrong with it again. All right? So that's the way we've been doing our industry. So the question in the hallway was, what can we do about this? How do we get 1,000 processor systems in the hands of all these researchers all over the world so they can tell us what we can do? This is I would say, historically, the biggest challenge facing computer science is, can we take advantage of this the sea change, going from sequential computing to parallel computing, where parallel computing is norm. This is a challenge for the research community, a challenge for our times. Can we step up to this challenge? How are we going to do that, given these things? And can we do this in a way we don't have to wait, every 4 years before we get the next try? Can we make it shorter so we can innovate, try new ideas out, throw the bad ones away, embrace the new ones, move forward, and not just architecture, but architecture, languages, compilers, applications, algorithms, the whole stack. How do we do that? So this is the thing that we came up with in the hallway, was the field programmable gate arrays. Depending on the size of the processor and the generation of field programmable gate arrays, you could fit 20 processors into a modern field programmable gate array. For those of you who haven't been paying attention, maybe 10 years ago it took 20 FPGAs to build a processor. It's the other way around today because of Moore's law, as we just heard about. So if that's true, then if we could find hardware that could put 50 of these together across a lot of boards, we could have a 1,000 processor system. Now, it's not going to run at a real high clock rate, but we could still have a 1,000 processor system. And so what the cabal got together, we did the secret handshake, and we said, okay, we're going to create an open source effort. We're all going to get together, contribute our time to create the logic design to load up those 50 FPGAs so that we can get a 1,000 processor system. And as we could do any instruction set, let's try and do instruction sets that have a lot of software, cache coherent, whatever we want. And so we agreed to do that, and we came up with the name RAMP, which stands for Research Accelerator for Multiple Processors. So why is this interesting? So to try and make the case, here's a bunch of characteristics on the left that you might care about. And what's interesting about this is performance is at the bottom of the slide. And there's been almost no computers ever invented for which, starting out, performance didn't matter, right? Sometimes that was the consequence of the design. But this is the beginning. Performance is at the bottom of our list. So what could we do? We could buy, a real expensive, to do this research, a big SMP, the old SGI days. Well, the problem with that one is it costs too much money. We can't. That's just out of our league for if we want to get to a lot of researchers. So clusters are pretty exciting, but it's at least a factor of 10 cheaper, but the cost of operation, the cost of space makes it, and it is millions of dollars. Not that many people can get it. So what the architecture community has been doing for the last decade or so is simulating on a PC typically. So the bad news about that, it's really great. The cost is amazing, and cost of ownership, all these things are wonderful. It's the two things that we care about the research community is first credibility. Do you think you're going to convince you've got a great idea for a 1,000 processor system that you're running on your desktop? That may not be believable, and you get 0 gigahertz, right? It's just not fast enough. So the thing that got us excited in the hallway was kind of the combination of these two things, that field programmable gate arrays get you lots of the good stuff from simulator. It's not almost free, it's say hundreds of thousands of dollars, but at $100,000, a lot of people can afford it as opposed to millions. And the performance isn't great, but it's fast enough. It's fast enough. And so that's why it gets a good grade, and that's why we're excited about it. So it's both a simulator and the flexibility, but it's fast enough and credible enough. It's the CAD flow is similar for FPGAs as it is for real hardware, and it's fast enough that you can run whole systems and get the answers overnight. You don't have to wait weeks for the answer. So that's the bet for RAMP. Can it keep up? Well, we just heard from Xilinx. These guys bring out new chips all the time. I think if we look over the history, it's about 18 months per generation FPGAs, and then more or less double the number of CPUs, and they get faster. But in terms of keeping up, this is not an FPGA supercomputer. This is an emulation system, an accurate emulation system. It's like a simulator, and then it's parameterizable and stuff like that, but it's fast enough that you can run 1,000 copies of Linux on 1,000 processors. So slower is okay as long as it's so much faster than 1,000 times faster than a simulator for a parallel system. So for this is a point I want to hammer in because I've gotten feedback on this. For us, success requires, like a simulator, psycho-accurate emulation of a parameterized design. So that's going to be a first-class bullet for what we're doing. One of the reasons is for the research to be believable, but also so we can run standard operating systems and databases so we can keep track of what it thinks the time is. So this is a high priority characteristic of RAM. So when we got back from the trip, we knew that the guys at BWRC, John Wawrzynek, had been building they're on their second generation of scalable FPGA design. And we got back and we said, well, what did we want and how well did B2 look for it? And it looked just about perfect. It has, this is the B2 design. It's been done, it's working for almost 2 years now. It's got 5 of the Vertex 2 FPGAs on it, lots of memory bandwidth because it's the second generation and it is important, tremendous amount of network interconnect on it. The only downside is using an older FPGA. I mean, the hardware worked, the FPGA was older, but that was certainly good enough. And then the most important thing from our perspective is you can connect a lot of these boxes together so you can get a big system out of it. And so perhaps this thing would cost $100,000, and kind of amazingly, if it's 1,000 processors in that, it's kind of a watt a processor, $100 a computer for a scalable design. That's almost everybody. It was great to see a storage talk at Hot Chips. Usually storage doesn't get so featured, but you know, RAMP could emulate storage as well. We need the capacity, but boy, the one thing you can get today cheaply is capacity. This is something Sun announced recently, which is 24 terabytes of storage at less. So we could put and it's just a few rack units high. So we could stick one of these things, their nickname Thumper, on top of that, and we can emulate the disk like virtual machines do as well. So all we need is the capacity somewhere, and we'll emulate how disk would act and seek times and all of that stuff. So, but is this really going to work out? Isn't there going to be bottlenecks? What's the performance going to be like if you really have, hundreds of processors in this box? Do you have enough memory bandwidth? So let's go through the calculations. So the reason it works is the processors aren't that fast, and the bandwidth of memories of modern memories is pretty hard. So for every FPGA, there's 4 banks of DDR2 400. So that's 12 gigabytes of memory bandwidth. And even if we assume 16 microblazes running at 150 megahertz, if you do the standard CPI calculation, that would only be 2/3 of it. But that's assuming no caches at all. That's just as if everything had to go to DRAM every time. If we stuck some caches in so that we could reduce the amount of memory bandwidth demand to that, we drop the memory bandwidth dramatically, and so then it's, we're using 10% of the memory bandwidth or something. So this is just an example of this new kind of thing. If we're doing system emulation, what we're trying to do is keep accurate clock cycles, but when it's running, we'd like it to run faster and be efficient, so there's stuff that we would do for it as well. Okay. Status, what our vision in the hallway was, we got to capture the minds, win the hearts and minds of software people. So we're going to try and make it as attractive as possible. Software people, so we thought vanilla as possible. The instruction sets, run operating systems like Linux, or Solaris. You can trace anything. What can we do to make it attractive software? But all of us had our own secret plans of what we would do with it. And here's examples on the slide. There's data flow designs, transactional memory, data flow computer, there's distributed data centers, all of us had our own secret agenda what we want to do this thing for, but we'd agree in this cabal to deliver this thing to try and be attractive to software. So one of the things we thought would be important for software is not to pick one instruction set, and so we said we would be ecumenical, embrace them all. So how's that going? Well, both IBM and Sun have signed up, as well as Xilinx for its microblaze. Sun, in March, has made the Niagara, their latest microprocessor, available to anybody, including us. In discussions with IBM, I believe we'll eventually get a Power 64-bit design, that architecture, either from IBM or somebody else. We had a great conversation with Chris Brown at Tensilica. I think that's a customizable RISC design that works. We've had, with ARM, a really great meeting. I would think that might turn out. We don't have anything. We haven't talked to MIPS, who have been good friends in the past. The only play, we struck out on the x86, but everything else looks promising. What we decided to do, since we were a distributed project and we're going to try and be our hardware guys are going to try and be the heroes here to the environment, was all of us were going to coordinate together, but this didn't have any funding for graduate students, and we were going to be geographically distributed. So we kind of decided at our last get-together that we'd reorient to give 3 examples of RAMP, and that's what we do, and those 3 examples would all share the common infrastructure. So the 3 examples are transactional memory RAMP, which Kozyrakis here at Stanford is leading. Message passing ramp with John Wawrzynek and I are leading at Berkeley, both for the MPI style supercomputing and then for internet services, with LAMP standing for the Linux, Apache, MySQL, PHP software stack, both internet and supercomputing MPI. And then Troy and Ho at Texas and Carnegie Mellon have agreed together to do a more standard shared memory cache coherent design, and that cache coherent ramp. So we're going to do 3 different examples over this next year to show what ramp can do, and we're going to use the common infrastructure across all these projects, and that's the way we're oriented. So what are our milestones? We're going to decide on the first instruction set next month, and those are the things we're going to care about. Does it run Linux? How big is it? Do we get the verification suite? Configurability? How's the licensing going to work? That's our first one. We're still going to try and do all the ones on that slide. Our goal for the next retreat in January, when we all get together from all over the United States, is 8 board systems, which depending on the design will be 64 to 128 processors. A year from now, a little bit less than a year from now, we're going to get together again, and we'll have increased the number of boards, double number of boards, number of processors, and we'll start using the Vertex 5 design, which you just heard about on their much smaller boards that they did. What the vision that originally from the hallways at Ramp was that we would all get together and do this development over this next year or so to get the ideas and get it working. But then so that other people could buy it, we would try and find some third party, redesign the board using the latest parts. These are Vertex 5. We're in Vertex 2, so it's 2 generations later. Have a board that anybody can buy, so you don't have to come to Berkeley to get them. You just write a check, you get the board, you download the stuff from the website, and you're ready to go for whatever you want to do. What's the status of these 3 different flavors? I guess we got the status of 2 of them. The one here at Stanford is all ready to go. It's using the hard-coded PowerPC cores, the ones that are already on the chip in the Vertex 2. And it's running, it's got 8 processors going and running transactional memory. It works. It runs the benchmarks. And it's got this first thing that is inspiring us. And as soon as it started working, suddenly they had something 100 times faster than anything they had, just with the 8 processor system that's running there. The Ramp Blue that's being done by John Wawrzynek and I at Berkeley, it's got, instead of using the hard-core PowerPCs, it's using the soft-core microblazes. We've got 8 of those per FPGA, 8 modules times 4 FPGAs per module is 256 modules. It's running at 100 megahertz. This is the connectivity. This picture is relatively recent. I think what's it now? It's 4:30. Yeah, this picture's from 3:30. I think it is. So we use the talk deadline to inspire work, and we've got all the diagnostics are running, and the applications as of 3:30 weren't quite working yet. So we think later this week. We also investigated inside the microblaze, the Leon design. If you know about opencores.org, they have a 32-bit version 8 Spark, and we looked at that design. We think on one of these modules, we could do 16 processors at 50 megahertz of the Spark, and looking at the Vertex 5, that should go up about a factor of 4 in number of processors and more than a factor of 2 in megahertz. And we are exactly at that line in the prior. We exactly got a 30% reduction in LUTs from version 2 to version 5, and we also have similar results looking at a power organization, a 30% reduction. So that 6-input lookup table versus 4-input lookup table looks very promising to us. We did get an infrastructure grant, which means we'll pay for kind of staff and some, pay for staff is what it means, no graduate student support. Several of the people got support from IBM faculty fellowships. We do these 3-day retreats. We get people from industry and us together. We've done 2 of them. We've got 2 more to go before we declare victory, and short courses here. One of the things that Krste Asanovic led while on sabbaticals in Berkeley is what I call a hardware scripting language, or what he calls a hardware linker. But if the idea is to take these modules from all over the United States and put them together, how are we going to do that? And the idea is we are going to, they invented a language for it, a ramp description language called Riddle. And the idea is it will generate the code, say Verilog or VHDL, to connect these components together from all over. And I think that's one of the interesting ideas. People ask us, what about existing things like QuickTurn? QuickTurn is really invented to create, really monster CPUs and do the simulate every gate. That's not what we're about. The idea is the processor is the building block, and how do we connect them together? So besides this ramp, so when people ask us what you can use ramp for, it's kind of hard for us to say, know what the limits are. Suppose you don't give a damn about parallel processing. Ramp is then still pretty damn exciting. You got Linux, you got a standard instruction set. What could you do with that? Well, you could trace anything, even what's going on inside a virtual machine on top of the stack. Suppose you have ideas on security, you could connect one of these things to the internet with your security enhancements and hardware and see what really happens. How about you care about reliability? Since you control all the gates, you can insert faults anywhere at the right clock cycle and see what happens. You could do switches. Suppose you care about quad floating point. Where are you going to get hardware for that? You could do that. But it was invented to help with parallel processing. And so what we're shooting for is this common artifact that everybody would be using. And we can tape out every day, right? And the build time for the next isn't years, it's minutes. Think about it, our friends at MIT say claims that those of us on the West Coast aren't always sure are correct, say, hypothetically. Well, we could just sneak in, FTP their design, run it on our computer, run our programs, and see how fast it really is, right? And publish our own papers on that. Not only could we check other people's research, this would be pretty damn valuable in the classroom. If we're going to revolutionize computer science education for parallelism as a first-class citizen, okay, what are they going to run on? Well, 2 processors is better than 1, but wouldn't it be better if these people could use 100 processor systems? It wouldn't be better if they could start using transactional memory today, not wait 10 years until there's systems out there with that. You can try these ideas out. And if the companies who are trying to influence have these boxes, it's a lot easier to convince people if they could run their programs than if they had to run their papers. And as I think about it, what's probably going to happen if we don't do ramp is they're just going to bet on one of these research ideas, build it and ship it, and cross our fingers and hope it doesn't screw up this parallel revolution. So we see ramp as this multiprocessor watering hole. This killer app is kind of anything in computer science. And what we hope the watering hole will bring these people together from all these different disciplines to talking about what I can think is the most important problem facing us in computer science, is making this parallel revolution happen. And I can imagine those of us who were around when we really loved the VAX and Berkeley Unix and everybody used it and we all shared the code and everything, I think that could be recreated again around ramp. It's gotten, you remember when it started, the word spread like wildfire, I think, because a lot of people are worried about this problem. We've got a lot of supporters. So last slide before questions is, we need it. Not only do we need it, we needed it yesterday. And what it is, it's not an FPGA supercomputer, it's an emulator that runs fast, and it's relatively cheap. By agreeing to standardize on the B design that John led, we don't have to, otherwise everybody's going to do all their own boards. Let's just all agree together. And we get to be the heroes by helping people in our community by supplying the gateware rather than the software people doing that. Emulate anything, trace anything, tape out every day. Let us explore not only the architecture space, but the whole language, algorithm, software space as well. And hopefully it'll be this multiprocessing water hole that really does ramp up parallel processing. Thank you. Guri.
Hi, Guri Sohi, University of Wisconsin. First, I'd like to make a comment. Thank you very much for going the simulation way. Being from a group that has been pushing this for 15 years and always getting pushed back from Berkeley, Stanford, and MIT for not building hardware, we are very glad to see you do this. Must be something in the Madison air and water. So I'm glad to hear you say that.
Okay, so if you consider the simulation, then this is
the revelation happened in Madison. Thank you.
Okay.
So there's a issue about credibility. Okay, that you claim that building credibility is important. I think what we are moving from.
Do you think credibility is not important?
Let me finish my thing, Dave. It used to be that industry would say, convince us. We got enough stuff to do, convince us. Today you talk to people here, they'll say, we are desperate, tell us what to do. Credibility is not going to be an issue going forward. Innovation and ideas are going to be. So why do you believe credibility ramp will allow you to get some kind of credibility?
This is too
Why is
easy
it
a question,
important?
Gary. You must have a harder question on that. Okay. I think you can't, I know the people of Wisconsin are not going to do incredible, non-credible research. I know they're not going to do that. I think in talking to, so we've asked this, we have these retreats, we have people from industry ask them, so what do you think? Do you think if we do the CAD flow where we're doing gate designs and stuff like that, we're starting with industrial strength processors as our building block and connecting them to the other, do you think that results done that way are more credible, more believable than doing simulators? And they say yes, they agree with that, because it's just too easy to cheat in a simulator. In a simulator, you can go forward in time and accidentally grab something, right? It's much harder to do something like that in what we're talking about. So, the industrial people tell us, yeah, they think it's more credible. I think, I agree with you, though, that industry is absolutely desperate, but they're going to bet. This is not going to be like just the supercomputing line that's going to go parallel. This is going to be the main line. I think there's reasons, the sooner we can get results where they're willing to try something, and what the figure of merit, I think, is efficiently programming highly parallel systems, right? The sooner we can do something to help with that, to get them to invest in that, the better it'll be for the whole industry. So I think the credibility will, I can see FPGAs making it easier to make the case for embracing an idea. I'm afraid if somebody has a really great idea and it's only done in software, it'll just take longer for that idea to be embraced.
Well, one other point was about, you said it was faster we allow people to build software under these architectures.
Right.
You got to believe going forward, software cannot have any notion of microarchitecture, timing, or any hardware details. Okay, because if you start building software, that assumption is doomed. So why would I want to have microarchitectural details in your emulator? Why not just simply execute an block of instructions without any microarchitectural details?
We're trying to put the thing that we think we're trying to create the watering hole. So we think the thing that'll be most attractive is we say, no, this isn't Dave Patterson's processor design. This is IBM's processor design. And it's real and industrial strength, and it runs fast enough that, it runs so much faster than simulators, you can get real work done. So we think that's the most attractive thing to do. It may prove, and if it turns out we don't need all that stuff, what we're trying to do is evolve the whole field right forward. So if it turns out in the beginning we put all the stuff in you don't need, and everybody agrees you don't need it later, well, that's what's the beauty of ramp. Okay, don't do that. And all the infrastructure, all the $100,000 boxes are still incredibly useful, even if we don't need that detail.
Thanks.
Okay.
Richard Zolkowak in NVIDIA. You said you get this question asked all the time, but you skipped over the answer so quickly I didn't hear it. And that was, why isn't the existing emulation type boxes, the quick turn and the...
So like a quick turn box, which costs like $5 million, doesn't have a clock. Right? So what we're trying to do, we're higher up. We're a lot higher up in the food chain. The NAND gate or the transistor of the future of this style of architecture is the processor. All right, that's what it's going. And what QuickTurn has been focused on is how do we accurately cover all the gates in this design. Okay. So I think that this might lead to startups that have system emulation as the focus, and and I'm sure if they did that, they get the questions as why you're not like QuickTurn. But I think that's the fundamental difference.
So if I had a $5 million QuickTurn box sitting around and I couldn't use it for what you're proposing? I can't model it at a high level?
You could probably use it. Yeah, if you had one, you could probably use it. But, if we're going to get this in the hands of... so the full vision now, besides the ramp box, is Xilinx, to its credit, and probably to it, they sell boards that have an FPGA in it for $300. The project we were doing in this last semester, we ran out of boards. Oh, God, in the middle of a class, we don't have enough boards. What are we going to do? So one of the graduate students went to Xilinx, gave him the credit card number, and the board showed up 3 days later. And and that allowed him to build another 4 computers, right? So this is a different kind of, this is kind of a, if you had to invent something at this time, how in the hell are we going to do architecture, hardware research? Well, we need something that's cheap and flexible and stuff like that. And the field programmable gates are it. And the fact that we could, a single board design for $300 is actually a pretty exciting research vehicle.
Okay.
Hi, Fritz Kruger, ATI Design. I was wondering if you could talk about the interconnect fabric on the B2 board as well as the backplane, and how it would be possible, or if it's possible, to emulate other interconnect fabrics.
It is. Let's take it offline though, because we're getting a little.
I don't get to ask a question. It's got 20 gigabit. It's got 20 on every board has 20 10 gigabit ports, and that's what comes off the boards. And then how do you connect those boards together? You should talk to John about that. But it's got a surprising amount of interconnect. Yeah. So you can do a lot of designs.
Yep.
Do I have? Keep going.
Yeah. Why don't you we'll get
Yeah,
through this.
I think it's a neat idea, but I'm worried. Running at 100 megahertz compared with a 3 gigahertz processor, you less than 3% of the sequential performance. And that could be an enormous problem in terms of credibility and really running anything of some reasonable size.
Well, that's why, Carl, that's why I said the accurate accounting is the thing to focus on here. So just like a simulator runs at what, 1 kilohertz, right? That doesn't really matter. What matters is you care what it says, how many clock cycles did it take to run, right? That's got to be faithful and credible, all right? So that's what we say. We say we think it'll be more, the clock cycles we say it takes you to run, whatever clocks, you say you figured out a way to do 5 gigahertz clock cycles. Okay, you say you can get to memory in 100 clock cycles. Great, we'll put that all in. We'll tell you how many clock cycles it takes to run applications and trace anything you want while it's doing. Now, the difference is instead of running at 1 kilohertz, we're running at 100 megahertz, so we're running 100,000 times faster. Yep. So that's the bet, all right? And so we think enough, at least for researchers, like we've talked to people as a company. A lot of companies would like to have this box today. If I dumped one of these boxes with a 1,000 processor thing running Spark at Sun Microsystems near the OS community, they'd drop everything they were doing and try and see how Solaris scales to 1,000 processors. It'd be, wow, how fast, where are the bottlenecks? You know? So the flip side of hardware people doing something when the box shows up, don't do anything when the box shows up, is when the box shows up, they do something, right? Yep. And we believe that this will claim its hardware, not a simulator, will claim its hardware, and they'll say, okay, and try and use it.
Right.
So that's the
But for something like Solaris or other software things, the key thing is not how many clock cycles it takes. It's, can I try out my big software idea? And running so slowly, you may have a problem.
You know, the guys who won't want it, physicists won't want this. They're going to want to solve their problem. People who are interested in parallel research and want to see what the future is going to look like, what would my application run on a computer of the future? This is the way to answer that question.
Two more quick questions and quick answers, please.
Oh, yeah, quick answers. I'm famous for my quick answers.
So I actually had the same question. So first of all, yeah, the running Solaris on this at 100 megahertz would not be a problem. We would love to do that.
Right.
Will you have to slow down DRAM since you're going to use standard DIMMs, I imagine, and your processor is 1/30 the speed?
Yeah. So what we'll do is we want the fastest, the most cost-effective high bandwidth DRAM so that the emulation doesn't take too long. But the question is, if what we just said, well, you know, it took you an hour to run that program, that will be misleading because we have 100 megahertz processors and 400 megahertz DRAM. So what we say, that's not what we say. What we say is, in your emulated clock cycles, it took an emulated 10 minutes to run because we're giving you the accounting like a simulator.
Right.
So if we don't do the accounting right, we can mislead you and have non-credible results.
Or you could mislead us in the sizing of some of the buffers that we need.
Right.
When things.
So we believe if we do this design right, you will see subtle details like your buffers weren't big enough, and you're getting buffer overflow, and the machine's grinding to a halt. And because it's a similar CAD flow, the same thing will happen. That was my short answer.
Yeah, I have a comment about your statement that it should be much easier to use for, let's say, for some kind of research architecture. Because you do it in FPGA, you still need to develop RTL, and that takes a lot of time. And sure, you save on chip fabrication, but you still have to hire, I don't know, number of graduate students to do the design and verification. So.
Yeah, so I'll try and do this quickly, but how in the world could you build an operating system without a company like Microsoft? That can't be done, right? You need thousands of programmers. The open source effort is what's our inspiration. So we are collectively across these 6 institutions, these 10 faculty, and then I don't know how, and another 100 graduate students are collectively going to do this. And I think open source works when you understand things well enough that it doesn't take professionals to do it. So we claim there's lots of pieces, processors, switches, and stuff that are well enough understood that we can do a credible design, and in this open source model, we'll be able to successfully build this thing. But that's, you know, well, will that be true or not? We'll find out in the next year.
Okay.
Yeah, sorry.
Thank you, Dave. The speaker of our final paper for this session is Takashi Yoshikawa. He has a MS degree from the Tokyo Institute of Technology that he received in 1997, and then he joined Toshiba then and has been there for these last 9 years, where he's been a research scientist of computer architecture. He worked as a verification engineer for the cell processor in 2001 through 2004, and since then has worked on this dynamically reconfigurable architecture that he's going to describe today.
Thanks. So good afternoon. I'm Takashi Yoshikawa. My presentation is about an implementation of hardware accelerator using dynamically reconfigurable architecture. So this is the outline of my presentation. So first I talk about the motivation for this research. The motivation is obviously multimedia applications are getting more and more important, so we need a better solution for such applications. Currently, there are 2 solutions for them. One is based on a processor, and the other is based on a hardware engine implemented as ASICs. But processor solution is not efficient even if simple operations are used, because data must be aligned and shuffled in memory before actual simple operations are applied. In addition to that, simple operations don't always fit multimedia applications. On the other hand, hardware engine is efficient, obviously it is, but it's not so flexible. So we think that reconfigurable logic may solve these problems. But if simply replace ASICs with FPGAs and implement the same hardware engine on them, then the size of such a chip could be much bigger than the original hardware engine. So to minimize its size, the logics and networks must be highly reused for various signal processings, and at the same time, to achieve a better performance, overhead of loading configurations must be covered with processing time. So for all these reasons, we propose dynamically reconfigurable architecture for multimedia applications. Now going to the architecture overview of our accelerator. This is the entire block diagram of our accelerator. The accelerator consists of these units on the right. I can see the pointer. Okay. And it is connected to a host processor via DMAC. There are 4 dynamically reconfigurable execution units inside the accelerator. They are formatter 0, formatter 1, AX0, and AX1. They are connected together via inter-unit buffer to form a network of data processing. Initial data coming from this I/O buffer and processed at this network of data processing, and the final result is written back to I/O buffer by write control unit. Now I'll show you in detail behavior of our accelerator step by step. Before it starts data processing, initial data must be transferred from system memory to I/O buffer by a host processor. That is done by a request to DMAC. If a code for that data does not yet exist in a code buffer, a host processor must also transfer the code from system memory to the code buffer. And after a data transfer and the code transfer are done, a host processor kicks this DMAC, and that triggers a code transfer from code buffer to these reconfigurable execution units and write control unit. Here, a code consists of configuration bits and a microcode which specifies how and when those configurations should be applied to reconfigurable logics. So let's skip this slide. So now this accelerator is ready for data processing. Any initial data in this I/O buffer are fed into formatter 0 first by this I/O buffer control. And that data processed at the formatter 0, and the result is written to inter-unit buffer by output control. The data in the inter-unit buffer can be passed to any other execution units or write control unit. So inside the formatter, there are 5 PEs connected together as a form of 5-stage pipelines. Inside the PE, there are 8 16-bit ALUs and 1 shuffle unit. They are all dynamically reconfigurable, and their configurations reside in the configuration memory. Now, a I/O buffer control issues 1 ID and a valid bit along with data. When PE receives an ID, a group of configurations are chosen from configuration memory and loaded into ALUs and shuffled and used for data processing at this cycle. This ID is called a context ID, and the group of configurations associated with that ID is called a context. Regarding valid bit, it specifies whether this data processing is valid or not. Any result from invalid data processing will not be written to inter-unit buffer. These data and context ID valid bit go down this pipeline in sync. Oh, by the way, there are a couple of flow crossover switches, either input of this formatter or output of this formatter, depending on the type of this formatter. So inside the PE, shuffle unit only supports 4 patterns of shuffle required for butterfly operations. And each ALU can be configured separately. It has 2 outputs, and one of its output is a duplicate of either the other output or one of 2 inputs, depending on its configuration. So the inter-unit buffer has 14 buffers. The size of each buffer is 128 bit. Any execution units can write any of these buffers, but it can read only a limited number of buffers, as you can see in the slide. The select signal is associated with a context ID, so a context ID controls which buffers should be used to pass data from one execution unit to the other. Now, since each execution unit can write any of these buffers, it is possible that 2 or more write requests to the same buffer cause a conflict. This inter-unit buffer does not have any mechanism to arbitrate such a conflict. It is an accelerator code's responsibility of avoiding such a conflict. That is doable and easy for our accelerator because it does not support any conditional branches, which means a behavior of any code is always the same regardless of its initial data. So, and there are AUX0 and AUX1s in this accelerator. They are also reconfigurable execution units. The difference between AUX and formatter is that AUX can handle complicated operations such as multiplication or 32-bit operations, while formatter can handle only simple 16-bit operations. The AEX have only one PE because the size of that PE is much bigger than that of Formata due to the support for complicated operations. But there are bypasses available between AEX 0 and 1, so it is possible to make these AUXs work as a two-stage pipeline. So after a final result is written to interunit buffer, that data is passed to write control, and it writes that data back to I/O buffer. A shuffle is available before write control write that data to I/O buffer. And that pattern of shuffle is also controlled by a context ID like the execution units. So this is an example of a timing chart of our accelerator. As you can see, each PE changes its configuration in a pipeline fashion as it receives context ID. The pattern of context ID change is statically specified in the control code, so it does not support any conditional branches. And the execution units other than Formata 0 starts its data processing only when all the inputs required for that data processing become valid. So in this slide, Formata 1 is waiting for both A0 and B0 become valid when at the vacant cycle. Okay, now go on to an application example from H264 decode. This is an example of a signal processing from H264 decode. A program for this signal processing is on the right. This is the original code for that signal processing. Now, to generate a code for our accelerator from this original code, we have to create two types of graph manually. The first type of graph is called context dependency graph, as shown in the left side. This graph represents dependencies between two contexts. For example, context F01 on the top of the right produces the one of two outputs for F1. To create such a graph manually, you have to analyze at first which portion of code can be mapped to a single context of which execution unit. And you also have to consider how data can be passed from one context to the other. The second type of graph is called operation graph, which represents a configuration for each context. This example represents a configuration for Formata 0, context 0, and 1. So it contains all the configurations for 5 PEs and also contains a configuration for full cross-bus switches. After these graphs, two types of graphs are created manually, one of our tools called context scheduler can generate a code for accelerator automatically. This is the result of that schedule, and it takes 96 cycles in total for this signal processing. Now we are focusing on these two cycles shown in this slide to show you the execution image of two PEs in the next animation. At the previous cycle, both data are already valid, so a new context ID is issued to a PE along with the valid bit. So that's done like this. And when PE receives context ID, a group of configurations are chosen from this configuration memory and loaded into the LUs and shuffle unit. The shuffle unit is omitted from this slide. And data processing at this cycle uses that new configuration. So like this. These steps are done at the first cycle. And the next cycle, still both data remains valid, so a new context ID is issued to P0. So at this time, the new ID is 1. Then, after that, both PE receives context IDs and changes its configuration at the same time. But P1 is using a context ID 0. On the other hand, P0 is using a context ID 1. So they are using different context ID. Thus, the change of configuration and data processing are performed in a pipeline fashion. So now going to the evaluation about the performance and the area consumption of our accelerator. For performance evaluation, we use H264 decode as application. These numbers come from our simulator. It's not a real number. And first column shows a number of cycles required for decoding most demanding macro block. EDR means EDR number is just the total sum of signal processing time. So the difference between real cycles and EDR cycles represent the overhead of code transfer due to dynamic reconfigurability. The third number represents a number of cycles required for average number of cycles required for decoding one macro block when a real bit stream is used. And I wanted to compare this number with that of a real processor solution with similar operations, but since we couldn't find any official number for that, we put a very rough estimate for PowerPC G5 here. That estimate is based on a recommendation on the Apple's website, so that data could be far from accurate, but still I think our accelerator can be about 4 times faster than PowerPC G5 in terms of the number of cycles required. So this timing chart shows how the overhead of core transfer occurs. Actually, core transfer consists of 2 transfers. One is configuration transfer, and the other is a micro-core transfer. So as long as the time for signal processing is longer than time for core transfer, such an overhead never appears. And overhead starts to appear when the time for signal processing becomes shorter than the time for core transfer, as you can see in the slide as a compensation. Maybe you can see this later. You can check your agenda. So, but as you can see, if the number of configuration memories increases, this overhead can be mitigated because you can transfer these configurations earlier. So going to the area consumption. So this is the result of logic synthesis for our accelerator. Our accelerator is expected to run at the operation frequency of 300 megahertz. Gates count for random logic is about 390K. And almost the same number of gates will be required for flip-flop memory. This number does not include I/O buffers and core buffer. This is a preliminary results of auto layout for our accelerator. The area will be about 2 square millimeter if 90 nanometer process is used. Formatter 0 and formatter 1 occupies more than half of its area. So now, going to the conclusion. I presented an implementation of a hardware accelerator using dynamically reconfigurable architecture. The key to its efficiency is it can reconfigure each crossbar and 16-bit ALU separately. And that efficiency is not limited to the acceleration of H264 decode. It can also accelerate H.264 encode and other codecs by applying different configurations. And thanks to its dynamic reconfigurability, our accelerator can achieve better performance as shown here. We expect 30 frames per second with 3 accelerators running at 300 megahertz for decoding full HD H.264 video. But still, its gate count is 390K. That's thanks to the dynamic reconfigurability. So I think that's all I have today. Thank you for your attention.
Looks like we have one question.
Yeah, I had a couple, maybe 2 questions. This is Kiran from Advanced Micro Devices. The first one was, I don't understand how it's faster. You're saying only cycle counts, is it? In terms of actual time, it's slower?
Mm-hmm. Sorry,
I mean, it's like
hear.
3,000 something cycles at 300 megahertz versus 16,000 cycles at 2 gigahertz.
Cycle time.
So the G5 is running at 2 gigahertz, the accelerator is running at 300 megahertz, is that it?
This number is based on the recommendation that actually I have some backup slides about that. So it said that the upper side said that it recommends dual 2.0 gigahertz power Mach G5 to decode full HD size H.264 bit stream at the rate of 24 frames per sec. So I calculated the cycles, number of cycles required for decoding 1 macro block. That is about 10,000 for each core, and if adds up 2 cycles, it becomes about 20K cycles. But since our accelerator does not include any cycles for decoding syntax, I assume that it will take about 44,000 cycles to decode syntax, so I just subtract that
but
data.
That's what I mean, it's cycles, right? So it's 5.14 microseconds is Apple time. What's in terms of real time for your block? I mean, it's running much slower. So what are you gaining in terms of real time? Isn't it running at 300 megahertz, so it's much slower, right?
What's the cycle? He's asking about the cycle time for your device.
Your device is expected running at 300 megahertz.
So it's going to take longer than the Apple, right, to decode?
Decode, yeah.
Anyway, I have a second question or a comment based on. So
if you just translate these seconds, number of seconds to the number of cycles, and compare those cycles, our accelerator only required about 3,600 cycles for decoding 1 macro block. On the other hand, PowerPC G5 requires 10,000 cycles for each core.
Yeah, but I mean, I only care about the end time, right? That's what I was asking. But I mean, we can. Right. So I have a second question or a comment based on. Do you know a previous architecture by a non-existent company called Chameleon Systems?
Actually,
there was a previous company called Chameleon Systems, which had a pretty similar architecture. The reason I mean, if you don't know the company, then I have a different question. The problem, like you're trying to address is, I mean, the thing is the architecture is very similar, but the biggest problem is that you're trying to do a very custom design for a dynamically reconfigurable logic. What are you gaining in terms of actually doing it as opposed to just do a static design on an FPGA or a full ASIC design? Isn't it a lot more complex in terms of designing it? Do you really gain anything by designing a more complex design?
Yeah, it might be difficult to design the first chip for this kind of dynamic reconfigurable architecture. But if you design once this kind of architecture, it can be be used for various type of applications. So comparing to designing the hardware engine for each application, I think it won't cost so much effort.
Okay, thank you.